that you really can get started. And the first thing is that some of the computers don't work, but please tell us with a post-it so that we can fix it for next time. So the main problem is we don't know exactly which ones don't work, and that's why it is hard to tell the maintenance crew which ones to fix. The second thing is that the material that I'm going to cover in this book is accessible through my web page, and it's here. If you look at my web page, Teodosio Pérez Amaral, UCM, then you will find that there is a link here which is called abebu.com, econometria, and there you can find all the material for this course. So you can download it, you can access it anytime, you can share it with whoever you want. And if you want, you can try and see if you can find it now, because it's better to have the problem now than at home. You can download the first lesson and you will see. I'm going to do the everything in English because there are quite a few people who only understand English, and I guess English is a good practice for everybody else. It's going to be very simple. You will see that I am always going to repeat the same words all over again. So it's going to be very easy for you to follow. Maybe not the first day, but after a couple of days, it's always the same words. Of course, you are going to have also the material, and the material is going to be very helpful. I would like you to look at, I'm going to pass around this book. This is the basic book for this course. It's called Analysis of Panel Data. You can get it through Amazon or any other bookseller. It is very inexpensive because it is a soft cover, and it is really worth reading. There is a previous version, second edition, which you can find in internet in PDF. And honestly, there's not much difference. So you do whatever you would like. It is always nice for me. You want to pass it around, you look at it and then pass it around. It's always nice to have a paper because you can go fast from one place to the other, and it kind of gets into your brain faster. But if you want to use PDF, that's okay also. That's up to you. I think that at some point I had here the PDF of the book. So I may just drop it by. Angel is going to be working for us. Angel here, he's going to be if you have problems, you can talk to him, and he will be able to fix all of them. The password for the computer is alumno. It's going to be all the time like this. And you find the material in my web page. And then what I'm going to do, you remember, most of you were here during the first class. The first class was like the last part of the class of the workshop. Some of you were not in that class, and most of you have already forgotten what I said. So let's see now a quick review of that in English. The idea of panel data is that you have now a new type of data which is composed of cross-section and time series. It is very common. The real reason for doing this workshop is that the data is very common. If it was not common, just go have a beer, no? Because, but that's not the case. It's common all the time. So every time you reach a research question, it is very common to have panel data as a help or as the main source of data. So that's why we care about panel data in this course. What we're going to do first, go to the next, is to check what are the advantages and disadvantages. So let's look at the advantages and disadvantages. So do you hear well? Yes? Because now we are taping the classes, and we are going to put them up for you, so that if you miss a class or you want to see it again or whatever, or you want to share it, you can have access to each class by videotape through the internet. The idea of the advantages is that there is a much larger number of observations now, more variability, more and better information. So there is a lot less multicollinearity. We will see that in a moment. A lot more efficiency. These are questions that are more difficult to see. I will not mention this here, but I will do it later. Remember that I went through all of this already. There is a big advantage here of diminishing the problem of omitted variables. Say, this is a typical question of, there is something special about him that makes him different from the other people, whatever. So if we only observe his behavior once, we notice that he's different, we don't know why. But if we observe his behavior a long time, in a sense, all we care is about the change in behavior, the change. So the change, for a change you may be normal, no? But not for your level. So your level, maybe you are consuming high quantities of Coca-Cola, no? And you're not normal in that respect. But the important thing is how your behavior changes a long time. So that is one way of being able of getting rid of the omitted variable problem. So the idea is some variables are omitted, but those variables can be, in a sense, treated by taking difference. So difference is going to be a very important way of treating the data. So now let me remind you that I also talked about disadvantages, and the disadvantages are that we have problems because now the data is much more difficult to handle, and the estimation techniques are not so obvious. We need specialized software, and we need to be able to interpret the outcome of the software more carefully. So that is, not everything is an advantage. So there are some complications in terms of the data, treating the data, of the estimation of the models, and of the interpretation. So there are some difficulties. And the reason that there are some difficulties is this is the reason why we are going to do this course. If there were no difficulties, we wouldn't need a course like this. So if you look at the book by Xiao, you will see that he doesn't comment about the difficulties. But the difficulties are very, very substantial. So don't underestimate them. One big issue in the idea of treating panel data is the treatment of heterogeneity. Heterogeneity is very important. Heterogeneity in econometrics is something that you rarely hear about, but it is very important. It is central, it's crucial. There are two sources of heterogeneity. One source is the unobserved heterogeneity, the part of the heterogeneity that you don't see. That part can hurt you. And then the other part is the observed heterogeneity. And that is going to work for you because that is precisely in synthesized in the explanatory variables. So heterogeneity, which is seen or unseen. It's hidden or it's evident. The evident part, great, because you can use that heterogeneity to explain the behavior. If it is unobserved heterogeneity, then we have problems, because that means that this is like omitted variables. You may or may not remember the basic econometrics class, but in the basic econometrics class, they tell you that omitting relevant variables is the most problematic of all specification errors, because it causes bias and inconsistency. So omitting relevant variables is very bad, very bad. And omitting heterogeneity, very bad also. Omitting the unobserved heterogeneity that you always have to omit is very bad. So let's see now a few examples. Let's go back. A few examples of heterogeneity treatment. The treatment of heterogeneity here in this very simple case that I already talked about in the previous class is that assume we have 3 individuals, 1, 2, 3. We are talking about maybe income and expenditure in clothes. You have the behavior of each of the 3. The behavior is the data represented by the data on the individual. And the idea is that you have 3 individuals that are behaving, each one on its own, is behaving in this particular little model. In this particular little model, you have 3 individuals. One of them, number 1, number 2, number 3, one of them is consuming little. The other one is consuming more out of the same income, and the other one is consuming more. So the idea is there is heterogeneity. The 3 of them do not behave the same. They respond in a different way to the different inputs, in this case income, and they just do not behave the same. In this case, the lower part, the middle and the up, 1, 2, 3 individuals, the 3 of them have the same marginal propensity to consume, but different constant. And that means that they are heterogeneous. They have different output for the same input. And you see that the constants are different, small, then medium, and large. The constants are different, although the slopes are the same. You remember this from the other class? So if we take into account heterogeneity, this is great, because this is going to help us model the three individuals. If we forget about the heterogeneity and think that the 3 individuals behave exactly the same with respect to constant and with respect to the slope, then we have problems, because then we are pulling the 3 individuals together, and if you pull the 3 individuals together, you will get the red line. The red line is telling us that there is a common constant and a common slope that is common to the 3 individuals, but if you look at the graph, you will see that the common slope is like 3 or 4 times more steep than the individual slopes, and you will see also that the constant, this constant here, is way smaller, and negative, way smaller than the smallest one. So this is important to notice, that heterogeneous constants can lead to what? The main idea is you miss the heterogeneity and you get inconsistent and biased estimates. So you miss the heterogeneity and you're dead. You're dead in this particular example. I put you also some examples which I'm not going to repeat, in which show you that in other examples it happens the same. So pooling when there is heterogeneity is not a good idea. In general, it will lead you to biased and inconsistent estimates. So it's not a good idea. If there is heterogeneity, if there is no heterogeneity, so if there is homogeneity, then it is a very good idea to pool together, because that means that you're going to get more efficient estimates. You have more information on the same type of relationship. So this is the idea here. Do you have any questions? Because we went through all this in the previous class. So let's see, Angel, let's go to the next. Let's go to the next. And then it's just to remind you that we are going to be able to test for heterogeneity using the usual F-test, nothing special. So let's go. The inconvenience I talked already. I forgot about this incomplete panels, but you see that there are inconveniences from using panel data. I'm not going to repeat that again. Okay, you have that here. I want to assure you that reading the book is wonderful. The book is very good in all respects. So it is very useful to read at least like the first third of each chapter. Then it gets more complicated and a lot of formulas, and it's hard to follow. But the beginning of each chapter, and especially this chapter 1, it is delightful. So it will help you a lot to read this, and it will not hurt you. It will not hurt you. I assure you that it will not hurt you. It will be very good, and you can read it slowly at your own pace, but it is worth reading. We are very happy now in econometrics because we have wonderful texts. We have many wonderful texts, not only in panel data, but in other areas. No? It's not like in microeconomics or macro. They always fight. One text gets old, then the other one comes, and it shows like just the opposite solution to the same question. So this is not the case. This is very, very stable and very appropriate. And please try to read the book, because it's going to help and save you a lot of time. So I think that I can only do like a commercial. I do a commercial and I say, well, this is good, this is nice. But if you read the book, this is the real thing. This is the real thing. The book is, and this particular book is wonderful. There are other books also that are very good, So if you go to Baltagi or other books, excellent. Woolrich, all of them are excellent. But I am following this book, the Xiao, because I find it very, very pedagogical, very pedagogical. I think that this is, it is unbelievable how he can write things that make sense, that are short, and look easy. I don't say that are easy, but they look easy when you read them. So it's very nice. This book is wonderful. Then I went into talking about the two common models, the common models that are fixed effects and random effects. I am not going to cover this now, because we will see that in chapter 3. So chapter 3 is coming either at the end of today's class or next week. So I'm not going to repeat everything. But the idea is that there are different ways to treat heterogeneity, and there are some ways, like this particular model here, which is particularly simple and easy to deal with, easy to understand, and it is very useful because it is able to capture many types of heterogeneity that happen in real world. So this model here, the model about different constants and common slopes. The yit equals alpha I star plus beta xit plus uit. This is a wonderful model, very simple one, and we are going to have to work with this extensively because it's very useful. It's very useful. There are some other models like this one in up here, the common constant and slope. This is called the pool model. Pool means put everything together. And this is almost the same as the previous one, but with a common constant, only one constant for each individual. This one is like the basic model. It is not as good as this one. And I think that for typical panel data, it will be very strange if you could use this model. I have never seen it, but maybe there are cases. I've never seen it. Do you have any questions up to now? Then just to remind you, to tell you that in this case, in the case of the very simple model that I was talking about, you can estimate it using OLS. It is great to use OLS. MCO is in Spanish, but OLS is in English. And it is great to know that you can get unbiased and consistent estimates using OLS. It is very good. And the reason you can do this is because all the assumptions of the Gauss-Markov theorem hold. All the assumptions of Gauss-Markov. So all of them, I'm not going to remind you all of them. You can check in Google assumptions of Gauss-Markov and you will find them, but they are anywhere. So the idea is that OLS is a useful way of estimating this model. Remember what I told you in the previous class. In the previous class, I told you that there are data, models, and estimation techniques. There is some relationship between them, but there is no necessary relationship between them. So if you want to remember that, and that is very important, especially for those of you who were not in the first class, you remember that we have data, in this case panel data, we have models, in this case, well, the fixed effects or and then random effects, and then you have estimation techniques, and these estimation techniques could be many, OLS, GLS, many. There's no particular relationship between one and two and the others. Of course, optimality is what leads your search. You want a technique that is optimal for a given data set and a given model. But there's no, I mean, God hasn't tell you exactly how to estimate anything. It's just, you have to decide. Do you have any questions? So we'll go with this, we go fast with this because we already saw this part. And then remember there was another model different model for the same type of data, but usually applies to different samples. This is the random effect model. The random effect model, we already saw this, is a model which applies to different situations than the one before. And it is usually applied to situations in which you have a larger data set and a larger sample. In that case, you usually estimate it by generalized least square, not OLS, but generalized least square. Typically, you can do it is not compulsory, but typical. Then choosing about the models is something that you can do, that you have to do. But remember, if we are talking about choosing about models, like here, choosing about models, we are not talking about choosing estimation techniques. We are not talking about choosing about data, one by one. If we are choosing about models, then the idea is that you have to, if you follow the book by Xiao or other books, you will see that this is pretty much a theoretical question. If you want to choose about different models, it is you have to decide which type of sample you have and what is the behavior of the sample in relationship to the population. So this is a theoretical model. You don't have a number to look at. Now, if you look at the random effects model, of course, you also have some characteristics of the sample that make that model more appropriate. And that is that the identity of the individuals is not important, and this a large sample from a large population. So this is the typical situation for choosing between models, not other things, models only. And that is the advice of Yair Munlak. He's a Jewish researcher working in Jerusalem. Now I think I'm going to skip that one because we already saw all this. So the next, and we are going to see it again more slowly in chapter 3. Here, in this situation, we wanted to talk a little bit about Hausmann test. The Hausmann test is a test to decide how to estimate. We are not talking about data, we are not talking about models, we are talking about estimation. And the Hausmann test is different from the type of model that you have seen in the course or in the master's courses, because it's just having Hausmann test before here, in which course? No, but not in Spanish. So usually in other not panel courses, it is very hard to see the Hausmann test. Although the Hausmann test is a strategy for testing, not a panel data test. It's a strategy, a general strategy that allows you to test in general between two different estimation techniques. Typically, one is consistent, another one is efficient. In this particular case, it's going to allow us to test between whether to use a fixed estimator, OLS, or GLS. You want to use OLS or GLS in the random effects model. So Hausmann OLS or GLS in random effects model. that is what Hausmann does. And Hausmann does a test that is going to tell you how to estimate one model when you can choose between two different estimates, one efficient and one. So we're going to see all this more slowly in chapter 3, because the Hausmann test is very important in panel data. So we're going to see it slowly. So let's continue. And just the last, or next to the last question is here. What type of applicability does the panel data type of technique have? So because when one starts thinking about this, you think that it's going to be limited to a very small range of models, but that is not the case. It is applicable to errors of measurement in explanatory variables, dynamic models, simultaneous equations. For those of you who know more about econometrics, you will recognize these three problems as the big problems. These are like the big problems because the big problems means all these cause inconsistency. They are big problems. And they are classical problems. If you look at the books, econometrics books, you will find almost always in classic books that these problems are treated one after the other. And the reason is that they have a common structure. The structure is that there is correlation between error and regression. And that is the structure. That is what makes these three problems to be of the same nature. And this causes inconsistency of the estimate of the conditional mean, inconsistency of the estimates of the conditional mean, inconsistency of the estimates of the conditional mean. So the three cases, they are different, of course, they refer to different things, but they have the same effect, the same structure and the same effect. So these are bad situations, and we will see that we can deal with these situations using panel data in an appropriate way. And in general, we are going to use instrumental variables. Instrumental variables are going to be used in these three parts. Then we also have the possibility of using maximum likelihood, which we will treat but not in depth. Limited dependent variable, and then the problems of heteroscedasticity and serial correlation. And last but not least, we have the problem of incomplete panels. Incomplete panels means that there are some units that are missing. One observation missing here, another there. So we may have missing information. What happens when you have missing information? Well, in general, that depends. Depends on what is the source of problem. If the source of the problem is that you have lost information at random, then pretty much nothing happens. But if the information is missing with a pattern, with a non-random pattern, then you may have problems, because that typically may cause inconsistency or bias or problems in general. So this is the idea. So this is the, do you have any questions about this? If you have any questions, just ask. No, it doesn't matter that they are taping. We don't care. They won't see your face. You use a hood and then you can talk, no problem. Do you have any questions? No, because we already saw all this. No? So now that the conclusions is that the type of data is more and more commonly available. The computers or software are available. We have Stata 14. I don't know if is it installed in all the computers, some or none. Do you see Stata 14? Because some of them I know are 9. Eh? Yeah, but this is because the software is not installed in each computer. It's installed centrally. So maybe that these were not updated. But what about the others? 14? 14? Well, you have to put the sticker so that they see. 14? 14? 14? So some of them haven't paid enough. You have to pay more. No, it's this. They have. I will tell one answer and see what happens. But this probably like this, but it hasn't been updated properly. Vas a intentar. Este está. So we were very lucky with 14 because, as Paco can say, we asked for 14. They said no, and then after some time, Angel found that we already had 14. So it is weird, no? Weird, because the typical thing would be yes, and then don't get it, no? But the answer was no, and then get it. Very atypical, very atypical. So it's in good part due to Paco that he was fighting for 14, and we all thought that you had failed, but it appeared. Now the thing is that Stata 14 is used in many places of the university. It's not an economics type of software. It's used in math, it's used in biology, chemistry, many other places. And that is why they probably push for that. It is a very good software. It is very expensive software, and although they have lowered the rates lately, and it is now available in many places. It is available in many research institutions, but it is a little expensive. It's expensive. I know that it can be obtained through illegal procedures that I don't know. Honestly, don't know, because we have everything that we have is legal. We don't know if it can be obtained through other means. So let's go to the second. I think we want to go to the second chapter, because the second chapter is very short, and then we will go a little bit into Stata. How many of you have used Stata before? But not everybody, like half. Okay, so we are going to do an introduction to Stata from the beginning. And if you already know, well, you just refresh your knowledge. But we need to do things from the beginning, because this course is pretty much self-contained. So I'll try to explain everything that we need so that you don't get lost. So let's see now lesson 2. Lesson 2 is a very short lesson. It is a lesson about heterogeneity, but it is just to detect heterogeneity. How do you detect heterogeneity? How do you find out whether there is enough heterogeneity taking into account or not? This is an important lesson because two things. One, because it is used all the time to assess which models you want to estimate. That's one, choice of models. A second one is, and everybody does this. Everybody is going to work with this, no problem. Second reason is that there are a lot of tests, like heterogeneity tests, like change of structure, things like that you may have heard of. Stability tests, have you heard? Yeah. Yes, stability. A lot of tests like this are very easy to do in Stata using what I'm going to talk about. They are extremely easy. But I have never seen one of those done by students. I don't know. No explanation. No explanation. They are very important. They are very easy to do. They are very appealing, but nobody does it. I don't know. I don't know why. So let's see now, like the basics. Which are the basic idea behind heterogeneity, the treatment of heterogeneity. So first, some notation like in the previous case, but just to remember, it is very important, the notation in this part. YIT, Y sub lowercase I, lowercase I, lowercase t, and then t goes from 1 to uppercase t, I, lowercase I, goes from 1 to uppercase n, lowercase k goes from 1 to uppercase k. So there are k, capital K, explanatory variables. And the explanatory variables are slopes, and they do not include constants. Okay? Now we are going to use, just to start with, models that are linear in the parameters. If we are going to start with models that are linear in the parameters, then we are going to see models like this. Models like this. This is a linear model in the parameters, YIT equals x equals alpha star IT plus beta prime IT x IT plus u IT. It's important to remember the letters, which letter is which. Now, if you see, you have seen sometimes parameters with subscripts, but not parameters with two subscripts. No? Parameter alpha with two subscripts. Have you seen them before? Have you seen them in the other class? No. In the panel. But have you seen them? Two subindexes? Two is too much. No? 2 is too much. So it is important to know that 2 is too much. Typically you have 1, which is I, sometimes nil, sometimes none, which is no subindex. So this is a model that that is allowing for, I said, too much. Too much what? Too much? Observations. No, the observations are T, capital T times capital N. No, but here there are no capital T's, no capital N. So alpha IT is what? The constant. How many constants do we have? Times t. So we have n times t constant. N times t constant. And that's why I was saying, too many or too few? Okay? Too many. Yeah? Because if we have one constant for each individual and country, well, we have already explained everything. That is mean. So Modeling means simplifying. Simplifying in this case means getting rid of subindexes, using not as many parameters as observations, but less. Huh? You have to use as a few parameters as possible. So now, if you come to beta prime IT, is this the same case as before or not? Okay? Similar. Similar. Why is it similar and not the same? Yeah, so now you don't have n times t, you have n times t times capital K, which is a lot, a lot. It is even more than the number of observations, even more than the number of observations. Huh? We have K times more parameters than observations in this data vector. So that is way too many, way too many. So typically, this would situation up here would be a lot of heterogeneity or a little heterogeneity. Okay? A lot of heterogeneity, a lot more than that. No? So, however, if we want to use a model that is useful, we have to use how many parameters? Way too many or just a few? Just a few. No? We'll see how we do it, but just a few. Of course, this is economic. This is not other subjects. In other subjects, you can have hundreds, millions of parameters, and everybody is happy. But in economics, you need to interpret the coefficient as the result of economic decisions. And if you have hundreds, millions of parameters, what can you say? You cannot say anything. So let's see now the next. Here you have yet another model. Another model that I would like you to tell me if this is too much heterogeneity or too little. So let's check the model. We have alpha sub I, beta prime sub I, xit, uit. So how many alphas do we have? Capital N. No? One for each individual. No, it is important to know. It's one for each individual, or 10 for each individual, one for each individual. Then, how many betas we have? So, how many for each individual? K. Huh? So, is that a lot of heterogeneity or a little? Hmm? Well, that's a good that's a good point. She's a very tricky person. Good point. Less than before. But I didn't ask this. I was asking, is this too much or too little? Still too much. No, still too much. Because we have one alpha for every person, and we have k slopes for every person. That means that we have how many parameters? N times k plus 1. A lot. Now, the problem is that sometimes you need it, but normally you don't need it. It will be too many parameters. If you have too many parameters, it's like having too many friends. Maybe you don't have any friends. You don't have any, and you didn't know. Too many parameters means that you have to interpret the parameter. You have to say this parameter means that this person behaves like this. But if you have 250 parameters, you don't know really what to say. So let's see now some restrictions. Let's see that we need restrictions because the restrictions in this area for econometrics related to parameters, restrictions are good or are bad? Good if they are true. But if they are not true, they are bad. No? So appropriate restrictions increase efficiency. And inappropriate restrictions or wrong restrictions lead to bias and inconsistency. This is something that you learn in econometrics, no? In basic econometrics. So we are here. We are with too many parameters. She says that these are too many parameters. So let's try to impose restrictions. We want to impose restrictions that are accepted by the data, not that are rejected. We want to impose restrictions that are useful. And let's see. Some restrictions here are the following. This is H1 is a restriction. So what kind of restriction do we have here? I need some help here. What kind of restriction? Are we talking about what kind? How do you read the restriction? That the slopes are the same for all the individuals. How many slopes do we have? Capital K. So, but capital K is not 1 million. It's 5, 6, 7. No? A few of them, not many. And then alpha I. How many alpha i's do we have? Capital N. Okay. So now we are talking about capital N, which is more or less it's the number of individuals. Okay. Capital N plus a little plus K, few, not too many. So we can live with that amount of heterogeneity, because if you go further, one step further, what would be? If you go one step further and decreasing heterogeneity here, how would you do it? So you change the model, restrict the model to have less heterogeneity. How do you do it? Okay? The only thing you can do is erase the I and get one constant. And then how many coefficients we would have if you erase the I in total in the model? That's K plus 1. So 5 or 6, 7, few. Okay, so this is the typical model that we call pool. So this is the typical model that we call a model in which there is fixed effect or dummy variable least square. You look at the estimation. So this is the simplest model that we are going to deal with, because the pool is too simple. So let's see the next. And then up here we have a different model in which this is a possible model. Can you tell me what this model is? How do you read this model? How many constants? 1. And how many slopes? Many, but how many? So n times k. N times k. So this is a possibility. Does it have a lot of Heterogeneity or a little? N times k is like 100,000 times 6, 600,000 slopes. A little too much. So this is a model that is possible, that you know there, it's there, you see it, but it's not very much used at all. So it's better something that you better look at it carefully, but don't use it. Because it's not used. No? At least I haven't seen it used. Then, down here we have another model. This is called the pool model or the joint model. Again, this is a possible model. This is something that you want to see all the time, but this is not something that you seriously entertain, because it is very strange that you have a model like this. It is possible, but it is very strange. And there it says that one of the cases has little interest and all this. And then, yeah. Sam? Well, that is a generalization of this idea, and it is very simple, because all you need to do is use some dummy variables for some specific slopes and not for others. So yes, it is the type of model that it is used, but it is trivial to work with. So it doesn't entail any difficulty. Yes. Usually what you do is you may want to allow the possibility of a structural break in one of the variables. Typically one, maybe more. If you say one, you can say any number. So you can allow for the possibility of a change, of structural change, just using a dummy variable that adds like another column to the data. It is exactly the same as in the basic econometrics. It is not something specific. I am doubting to continue or not, but it is very basic. So this is not something that we are worried about, because it's easy to do. But I will have to explain using using dummies. It is very simple. Now, what I would like you to do is to think of how to decide which model is better. The idea for deciding which model is better in basic econometrics is using the sum square residuals. You can also do F-test using other versions, but the sum square residuals is more convenient. So let's think of the possibility of entertaining three different models. And the models, all of the models are nested. Nested means one is a special case of the other, and the other is a special case of the other. I don't know if you have heard about nested models. Nested? So what I'm going to do now is to write a very simple example of nested model. So the first I'm going to do is I'm going to write a model here, which is like more general. X plus alpha 2 x 2 plus alpha 3 x3 plus u, and then let's put the i's, all of them are i's. This is cross section, and this is going to be a model, and we are going to call this a general model. General means in relationship to what? Well, it is general related to this model here, in which there is no x3. So the upper model is general with respect to the lower model. So the lower model is nested in the upper model. It's a special case of the upper model. And then we have a third model here, in which this third model is nested in the second, and the second is nested in the first. So the third is nested in the second and first. And now I just wrote another model, the yi equals alpha 0 plus alpha 3 x3 I plus eta I. Now, this fourth model is nested in the third or not? Fourth nested in the third? No. The fourth nested in the second? No. And the fourth nested in the first? Yes. No? So you see that the relationship of nesting relationship is a relationship that is not that straight. I mean that easy. You have to actually read it and decide for yourself which model. The idea is that there are simple restrictions that convert the upper model into this, the second into the third, and the first into the fourth. Okay, simple relationships, and those relationships are entailed by this null hypothesis. The null hypothesis that converts the upper model into this one is alpha 3 equals 0. Alpha 3 equals 0 makes the first model the second. Then alpha h0 alpha 2 equals alpha 3 equals 0. That makes model 1 into model 3. And then another h naught alpha 1 equals alpha 2 equals alpha equals 0 will make the first model the fourth. So this is the way of defining nested model, meaning that a model is nested in another model when there exists a set of restrictions that convert the first model into the more general model, that convert the general model into a specific model. So this is simple. This is simple. The idea of nesting is very simple, and of course you may or may not realize that every time that you have used an F-test, you have been using always nested models. One model, the other model, using the same estimation technique, you compare them and get some square residuals to do an F-test. So the idea of nesting is easy. Now, how can we decide when we should use a general model or a nested model? So in theory, how can we decide when you can use model 3 or you should use model 1? When is it intuitively? Don't think in econometrics. Yeah? When do you think we can use 3 instead of 1? Yeah, so that's the idea. The idea is when Model 3 does as good as Model 1, which one should we use? 3 or 1? 3. Why? Why? To improve the efficiency. Okay, so that's the idea. So we should use a model that is smaller, less complex, to improve the efficiency. Eh? Efficiency is important or not? It is very, very important. Very important. So we do care a lot about the efficiency. If we did not care about efficiency, then what should we use? The general model or the specific model? If we don't care about efficiency, general. But general here or always? Always, no? We should use always a general model and don't worry about anything, no? But that is a complete mistake. What we are going to do is, as always, decide which model we can use, with the idea of using the simplest model possible, not the largest model possible, the simplest. And what we are going to do here is we can look in particular to the sum square residuals. Sum square residuals. The sum square residuals, what is better, a large sum square residuals or small? Small, no? Small. Okay, so, and what do you think? That the square residuals of a large model, which is smaller than the of the more specific models, or bigger? The larger model will always have bigger sum square residuals, always. Okay. Now, but assume that so this is going to be the sum square residuals here in the, so let's call it sum square residuals 1, sum square residuals 2, sum square residuals 3, sum square residuals 4. Okay? So these sum square residuals. So what is the relationship between sum square residuals 3 and 4? We don't know. We don't know. It is important to know that we don't know. Now, the relationship between SR1 and SR2, which one is bigger? 2, no? 2 is bigger. And 3, bigger than 2 and bigger than 1. Okay? So this is a necessary condition. Well, this is not the same example as I put here. So you don't have, this is a different example. Okay? So I'm making an example here. The idea is that a restricted sum square residuals is always going to be bigger than the unrestricted. So, but the question now is how much bigger? Because if they are kind of close, then we should use which model? Restricted or unrestricted? Restricted. And if they are apart, then which one should we use? The unrestricted. Okay, so now let's go and see an example. So the example that we have here, this is taken from the book from Xiao. It is, the Xiao is longer than what I'm telling you, and it's not so well explained. But what I'm going to tell you is like the main point. So let's see the next. Let's see what was H3 before. H3. No. So let's go up. Let's look at the formulas. Down, down, down. Okay, so now let's look at formulas like this. There are several formulas like this, and the idea of these formulas is that we want to, let's find the right formula, because there are many of those. Test of H4. No, H4. Let's look at H3. Now the thing is that I wasn't following this, but let's look at this particular formula F3. This is a pull model against the unrestricted model. The idea is we are going to check if two models behave more or less the same, or if they are behaving differently. The idea then is, let's compare the sum square residuals. The sum square residuals are going to be close when the two models are similar, and are going to be separated if they are not similar. So what I'm going to do now is to read the F-test in the way that all F-tests should be read. So in a general way, but very simple. So this S3 minus S1 is going to be the difference in sum square residuals of two models. The first model, S3, the first model has to be more restricted or more general? More restricted, because the difference has to be positive. So S3 is a model which is restricted, and we are going to compare these sum square residuals with the sum square residuals of a unrestricted model called S1. So you can check, because you have the in front of you all the material. So you can check and see which is S3, which is S1, so that you can follow, so you don't have to be looking at me. You can look in the computer also. So S3 minus S1. If it is big, then we reject the null. We reject the null of that particular restriction. If it is large, we reject. If it is small, we do not reject. Okay. So, but how can we know what is large and what is small? How can we know? But what are we doing with that? We want to be fair, okay? We want to be fair. And fair means what? We want to take an average, okay? So what are we doing with the number of degrees of freedom? We are taking an average. And what is an average of what? What is this number? N minus 1 times k minus 1. This is going to be a number of degrees of freedom that are tested. And that is why. So again, numerator says the difference between sum square residuals in relationship or in average with the number of restrictions that are being tested. All the F-tests that you have seen can be read in the same way that I'm saying, all of them. Important to know how to read an F-test. And then if you divide, is because you want to put it in relationship to something. You want to put it in relationship. And the relationship is what? What is the denominator? What is the meaning of the denominator? The denominator S1 is the sum square residuals of the unrestricted model. And that is always the case for an F-test, always the case. So you may recognize or not that this is the way to read the F-test, but it is. And then here, what are we doing? These are the number of degrees of freedom. Degrees of freedom of what? Of the unrestricted model. Yeah. You may know or not, but it is always the same. So whether you recognize it or not, that's a different story. But this is the number of degrees of freedom of the unrestricted model. So let's look at the unrestricted model. The unrestricted model has n times t degrees of freedom in terms of number of observations. So this is number of observations times number of time domain intervals, n times t. This is number of observations, okay? Number of observations. Now, this here is the number of individuals times k plus 1. Number of individuals times k plus 1. You know, how many parameters do we have for each individual? If we have n individuals, how many parameters for each individual? Now, for each individual, k plus 1. K plus 1. Okay, so now we know that this is a model, the lower model, is a model that has n constants and n times k different slopes. So now we know which model we are dealing with. This is the general model. So let's look at S1. S1. Let's see before. S1 is the unrestricted model. So let's go up. So it is this unrestricted model, the model S1. And then the other model, S3, is this one, the pool model. So now we were comparing two models. One model had k slopes times n individuals, and the other one had only k slopes. So what we have done now, let's look at the test. This test is going to tell us whether we should use S1 or S3. So it's going to tell us if we want a restricted model like S3 or we want a general model like S1. The way to decide this is always the same. The average difference in sum square residuals compared to the variance of the unrestricted model. That is always the same, always the same. Do you have any question with this? Now, if it does not reject, we could use the pool model. Pool means no, only one constant and k slopes. That is the pool. This type of test is readily available in Stata. So those tests are most of the time printed in Stata. The only problem is that you don't pay attention to them because they are in the lower part of the screen, but it doesn't matter. They are there. You can use them if you want. So let's go. Now you can do a lot of F-tests like the one that we have seen. You can do many of those. But the most important one is the one that compares the pool model with the fixed effect model. And that is printed all the time in the lower part of Stata. That is printed always. Sometimes some others are not printed always, but this is printed all the time. Do you have any questions for this? So we're going to see the examples as soon as we finish this. Relationships. Now let's see some of the conclusions. The conclusions are very simple, but sometimes they are hard to follow. The idea, and this is very important, that F-tests can be used sequentially. So you can use an F-test to go from here to here, and then an F-test that goes from here to here, and that, of course, you cannot use directly an F-test to go from here to here. But you can do tests sequentially. They can only handle nested hypotheses. And typically you perform the tests in order that go from more restricted model to less restricted model. The tests are not independent, and the idea is that any test that you make is conditional on the decision that you took in the previous test. But sometimes there are some contradictions between the tests, but the contradictions are more on how you interpret the test. Typically, the tests are correct, and the interpretation is takes some time, but it makes sense. You don't have to you don't have to be very sophisticated, but you have to be organized and know what is first and what is second. I said that many tests are printed by default, and the important idea is this one here. F-tests of structural change across time can be computed, and also across groups of individuals, countries, or firms. And the F-tests are performed using the sum square residuals that is computed by state. So let's see. Let's see the next. It says here that other types of tests can also be computed, like LM and likelihood ratio. I'm not going to talk today about Hausman, LM, or a likelihood ratio, because I want to do some practice with data. But the idea is that the tests are very flexible for panel data and for many other types of data, and they should be used at least in a routine basis. Not that you use 500, but maybe 3 or 4 in every work that you do. Finish. Okay. Now we still have some time, and I would like to talk a little bit about Stata. I would like you all to open Stata, and please notice that you can download the data from my page that Angel prepared this morning, and please download the data that is called wage pan. So it is wage pan, so panel of wages, dot DTA. And this is a basic panel data set that I am sure that will work in 9 and 14. At least it has worked every time that I have tried. Yeah, this is it open, just click on it. file. The first thing I would like you to do is let's look at the description of the data. The description of the data is in 9, it's on the left-hand side, and in 14 on the right-hand side. And if there are any other versions, I don't remember. But there is a description of the data that you can, there is a window that you can open, you can make wider and wider, and you can have information about what is the data. This data set is about wages of American male laborers in the 1980s, and it is about how the salaries of the different laborers are explained by their abilities and their different sectors in which they are working. So everything we care is about labor income. So now Angel is showing you what type of data it is and where can you get more information about those data. There is a lot of information in the material that we put up for you, and you may want to look at that information just to have some background. It will take you like 10 minutes and it will be useful because we are going to be using this example in the next few classes. And it is a simple example. It is a balanced panel, and it is very simple. Do you have any questions? Please, questions. So now we have the NR, personal identifier, year, and then if it works in agriculture, it's black, business, construction, and experience, Hispanic, poor health, hours, manufacturers. So what we care about in this particular data set is wage. Typically, we are looking at the hourly wage, and usually we use a logarithm transformation. So there is one variable which is called L wage, which is our dependent variable. L wage. So this one right here. This is our dependent variable. We can go back later to the description of the variables, but the next thing I would like you to do is look at the numbers, the actual data. The actual data, you can look at it by going to the editor. There are two editors. One is the browser, and the other one is the editor. It is better to use the browser, because in the browser you can do all kinds of stupid things, and they don't get saved, okay? And if you go to the editor and you change the data by accident, oof, you have to start all over again. And you don't want that. So I would like you to see how the data look. It is very important to look at the numbers. It is not trivial. You cannot just don't look at the numbers. You have to look at the numbers, see what they are, understand what they mean, and then you can do things with them. But you definitely need to look at the numbers. The numbers here start with NR. NR is number. And the number starts with 13, 17, and then 18, and then let's see how more numbers. 150, 162. Yeah. Usually the numbers go 1, 2, 3, 4, 5. Huh? Why do we start at 13? Any different? No, but the years are here in the second column. The second column you see 1980, 1, 2, 3, 4, 5, 6, 7, and then again 80. The years are in the second column. That is a possibility, yes. Or you may have a big sample and they only gave you a little bit of that sample. No, but the same idea, no? Same idea, sampling. But is that a strange thing or a normal thing? Strange or normal? Eh? That happens quite often. So we have a individual identifier, and then we have a year identifier, individual and year. This is giving us and giving Stata the structure of the data set. The structure of the data set is there in individual and number. Because the rest of the variables, you know, they may be there or not. Or you may be accessible or not. But if the individual identifier is not there, dead. If the year identifier is not there, we're dead. So this is gives the structure. And then the rest of the variables are variables that refer to individuals. Individual that works in agriculture or is black or is working in business, construction, and it has that much experience, is working in finance, poor health. So let's go to the right to see what other variables do we have. We have many variables, many explanatory variables. We have hours, married, a lot of variables. The dependent variable is log weight, which is there, is log weight. Then union is measuring whether he's working in a syndicate or not, in a labor union. So those are the type of variables that we have. Do you have any questions so far? So let's go now, get out of the editor and go to see the main points. Here we have the main explanation of the variables. Then we have here the output window, here the command window, and here the use command window. This is like four main windows of the data set. They can be changed in appearance, in color, size, and sometimes they disappear. If they disappear, you have to go to window and then reinstate the windows. They have the strange behavior of disappearing sometimes. Now, what we have to do is to work with Stata. But before working with Stata, I would like to tell you a few things. The first thing is that you have 4 windows. All of them are useful. There is a command window which is below, and in the command window you write the commands. Most of the times you don't know the commands. So how can you write the commands without not knowing? Two tricks. One trick is, if you have used something similar before, it's going to appear here. You click on it and it will reappear. This is recycling. Recycling is very important of the commands because it is easier to do that than to remember. Another idea is at the beginning and while you're learning, you should, instead of use the commands, which you don't know how to use them, you have to go by the windows. So the windows are very useful. There are fold-down menus, and the fold-down menus allow you to do everything, everything. So I know that a lot of people don't show how to use the windows in Stata courses, and that is the reason is that they want to be seen as smart people because they remember a few commands. But that is not the case. You have to use the windows, and the windows are much more flexible than just using commands. Of course, if you're going to reuse the commands all over again, then you have to go to the recycling. So what I would like to do is just for finishing here to write a simple model about logarithm of wage and then estimate. Okay, so let's go first to the statistics and then longitudinal panel data and linear model, and then linear model, and then what? Here. And then you come to this window. You come to this window that is the estimation window for Stata linear models using panel data. It is a very useful type of window. I want you to notice that there are many options, many options. So what are the possibilities that you remember the options of this particular window? The possibilities that you remember all the options of this window, not Stata, this window. 0. No way, you're not going to remember the options of this window. How about the options of the whole Stata? Impossible. Okay, so but you have to see correlation by if weights, standard error, robust, and then informes, maximize. So it's impossible that you remember all this, and this is a simple estimation window. So let's now look at the main window, and I want you to tell me which are the important variables for the logarithm of wage. So which are the variables that are going to influence the logarithm of wage? If we are talking about labor economics, anything that makes sense, what are the variables? Well, you may look here and see that they appear in order. Okay, so you may want to look and check here which ones may be important and which ones may not be important. So NR, the number, yes, no? Important, no? Why? It is a random number, so it doesn't make sense to use it. A lot of people are going to use it anyway. No, but it's like using your ID number, no? Well, you can use it, but it's not very useful. And then year. No, the year is already used in the structure. Okay, it is used already, so we don't need to use it again. So let's now look at other variables that may be important. Yeah, but where is ours? No. Now let's go in order, because so that everybody gets the same variables. The next. I see agriculture. I see black, black, maybe. Yeah, but this is the States in 1980s. So it is, there is a lot of racism in that time. Now, more with Trump, more. Black, maybe, and then construction. So you tell me. Experience. And what else? Education is maybe important, yes. Hispanic also, and which one? I don't remember that one. Which one? Union. Yes, union is that belongs to a union, to a trade union. Yes. In fact, this exercise is designed to test whether the union is significant or not. So, coincidentally, this is about what is the effect of unionizing on the salary of the workers in the fields of the state. So it may be important, maybe. And what else? Maybe, yes. Geographic location is taken care of by dummies, individual dummies that affect each individual region. And now nobody said married. Married, why not? Married is a very important variable when talking about the labor income. And the reason is that married people, we are more reliable than unmarried people. Yeah. No, I'm not kidding. It's true. In my case, it's true. No, the gender is not in this sample. So we don't have salaries for women. So it may be important, I'm sure, there is a lot of discrimination against women, but we don't have data for that. So do you have any other possible important variable? Hours? Hours is maybe important because why? Why hours? No, you have to say in loud voice. So it's the opposite. The opposite. Now, your salary per hour is going to be lower the more hours you work. Huh? Yeah. No. It is the number of hours of work per year, and the salary we are talking is salary per hour, and L wage is the logarithm of the salary per hour. Okay, so let's now run the regression, but let's use fixed effects. So what happened with fixed effect? There must be some problem because some variables have not been, the coefficient has not been estimated. So we have a big problem here. It's Angel is not doing his job. So now what we're going to do is say bye-bye until Wednesday. So you figure out what's going on. It is very simple, very simple. But you should figure out what's going on. You read a little bit ahead and you will see why it's happening and what can we do about it. This one? This one. Yeah, this one is pretty good. But you see, this S is the one that I was talking before. The one that is comparing the model of, yeah, one constant with many constants. So now you have to close and leave. I'm not going to tell you anymore. Yeah, please close and save everything. Save, because otherwise the next day you have to do the same again, all over again. You will see that you cannot save. I will tell you next time. Of course, it is crucial to save, but you cannot save.